Lesson 40 demo. In this class, we discover several theorems about definite integrals and investigate the area between two curves. What if the limits of integration of a definite integral are both the same number? We define the integral from a to a of f of x dx to b. Well, we know that if this is some number other than a, then this expression here represents the area between the curve and the x-axis from a to b. But if a and b are the same number, then there's no space in there. There's no there's no area to speak of. And so we just define that to be the number 0. What if the smaller number is on top? For example, what is the value of the integral from 2 to 0 of 6 dt? Typically, you'd expect to see integral from 0 to 2, but it could be backwards. So what does it mean? Let's go ahead and calculate the, quote, normal order integral 0 to 2. So thinking about that, I know that y equals 6 is just a horizontal line. And so the integral of this thing from 0 to 2 is just the area of that rectangle. So 2 times 6 is 12. Easy. Now we can imagine that this integral represents the distance a runner travels in 2 hours, that's the 0 to 2, if they are running at a constant 6 miles per hour. That's the 6 right there. You buy it? Area underneath that velocity curve, of course, is the total distance traveled in those 2 hours. We can then think of the integral from 2 to 0, that's backwards, as representing the distance traveled in reverse. You could imagine somebody has recorded this person running for 2 hours, and you decide to watch the video backwards, starting at the 2-hour mark in the video and ending at the start, the 0-hour mark in the video. And so if you were watching this person run backwards, you could make the case that instead of saying they ran 12 miles forwards, they actually ended up running negative 12 miles because they were going the wrong way. And so the integral from 2 to 0 of 6 dt is actually just the opposite of the, quote, normal ordered integral. And so the conclusion here is that we define the integral from b to a of f of x dx to b. Well, you just put them in the normal order. You just swap them if you are so inclined. But then you take the opposite sign. Okay, let's do a couple of examples. Evaluate this integral, 3 to 3 of x plus 2. As soon as I see the 3 to 3, I can stop reading. I know that an integral is 0 regardless of the x plus 2. Doesn't matter what the integrand is. Okay, b looks trickier. So first of all, the limits are in the, quote, wrong order. So I'm going to put them in the, quote, right order. And just do this integral first. And then we'll figure out what to do about the fact that the limits are reversed. So square root of 1 minus x squared, might not recognize it, but it is this curve. It is actually the top half of the circle centered at the origin with radius 1. We are interested in this orange thing for the integral from 0 to 1, here over to here. So we want the area of the quarter circle. So a quarter pi times the radius squared, pi r squared. Radius in this case is 1. So the area there is 1/4 pi. So what if I wanted the original answer? That's the integral from 1 to 0. Well, you just take your original answer and take its opposite sign. Negative 1/4 pi is the answer there. If you think about geometry of areas, you should be able to fill in the equations below. So the first one is the integral of f of x plus g of x. So it turns out this is exactly the same as the integral of f of x dx plus the integral of g of x dx. So it's important they both get a dx, and it's important that you copy the limits on both of them just like they were in the beginning. So really, really nice to do integrals of sums. You can just separate them into 2 separate integrals. You can do the area calculations completely independently of each other and then add them up at the end. Likewise, you can subtract independently to the 2 integrals independently and then subtract your answers at the end. Okay, constant, the integral of c times dx. So this one, if you think about the example we did up above, we had 6 from 0 to 2, right? And that was just 6 times 2, which was 12. So what is it in this case? Is it c times b? No, it's actually c times b minus a. The reason it was 2 wasn't just because there was a 2 on the top. It was because there was a 0 on the bottom. 2 minus 0 is really was really the time that was elapsed for that problem. Okay, it turns out for integrals, if you have a constant in here multiplied by some function, you are welcome to just do the integral of the function, find the area of the just under the function, and then multiply that area by the constant instead of thinking about a new function, which would be the constant times the original function. So constant multipliers can come outside of integrals. And some of these properties should really remind you of corresponding properties with derivatives. We saw that if you wanted to do the derivative of a sum, you could do the derivative of the two functions independently and add them at the end. Same deal with difference, same deal with constant multiple. Okay, part E is kind of a wonky one. Let's take a look. It says integral from a to c. It's the same function f of x in both integrals. So this is the integral from a to c plus the integral from c to b, and somehow we're supposed to write something meaningful down. Well, let's take a look at this picture below. So I will shade in this guy in orange. Integral from a to c is this area here. Integral from c to b is this area here. Oh, I see what's going on. We really could have just done one single integral, one single area calculation, f of x dx. And in this case, we could have really just gone from a to b. There was no reason to make that pit stop at c, right? It's just the total area of red plus green is really just the entire area from a all the way to b. No need to stop at c on the way. Okay, let's see if we can apply our new properties here in number 6. We're going to evaluate this thing by hand, and then we'll check the answer on the calculator. Okay, first thing I see is a subtraction sign between two functions. I like that because that means that I can do two separate integrals, each of them from 0 to 1. Each of them gets a dx. That's really important. Every integral sign, the Kirby sign, has a corresponding dx at the end, or be some other letter. And the subtraction property up above says that I can just do those two integrals separately and then subtract at the end. Okay, this first integral I can actually do. This is the integral of a constant. It's the property c right at the top left there. And so this is really equal to 5, that's the constant, times the difference between the limits of integration, 5 times 1 minus 0. Easy. That 3 is a constant multiplier, and I can bring a constant multiplier to the front of the integral, do the integral, and then multiply at the end. Okay, that integral would be hard, but we actually did that integral earlier today. It was pi over 4. So this is really 5 times 1 minus 3 times pi over 4. And that is our answer. And so you can see the power of taking this constant multiple outside. It made the integral simpler, and it turned the integral into one that we had done. We hadn't done this integral before, but we did this one, and so we could just multiply by 3 at the end. All right, let's see what the calculator thinks about this. Math 9, 5 minus 3 square root. So I'm typing it in as in its original form. Close the square root, comma x, comma 0, comma 1. And I'm going to get some decimal here, and then we're going to compare it to our answer, which means in a second we're going to type our answer into the calculator. 5 minus 3 pi 5 by 4. And very good. Which one is more accurate? Actually, ours is more accurate. The calculus doesn't know how to do exact areas, so it's really doing something like 5,000 rectangles, little teeny tiny rectangles. That's why it took some time. I don't know if you noticed, but it took a few moments for the calculator to come up with this approximation. This with the pi is the exact answer, so this is a more accurate answer. Pretty darn close, though. Close to each other.